Very good. All right. Thank you very much to the organizers for inviting me. It's an honor to be here today. As I'm sure other speakers have remarked, I feel I must apologize in advance. I was directed, like we were all directed to give a colloquium level talk to an audience of physicists, mathematicians, and philosophers. And at the beginning, Yang also added engineers and computer scientists. And I'm quite certain I have not succeeded at that goal. Hopefully everyone will find some part of this talk to be understandable, but I don't know that everyone will find all of it to work in that vein. So this talk is going to be about something called decomposition in quantum field theories. So specifically, my talk concerns examples of quantum field theories which are secretly equivalent to sums of other quantum field theories. So when this happens, we say that the field theory decomposes, and we can apply this to give insight into the properties of that theory. So when this is likely to happen? Well, first off, I'm primarily interested in quantum field theories in 1+1 dimensions because they provide analogs of quantum mechanics for string theory. Now, to get the real world from the 10-dimensional physics of string theory, what we do is we roll up or compactify the 10 dimensions on some compact 6-dimensional space. Now, if I compactify a string on a disjoint union of 6-dimensional space, or work with a stringy quantum mechanical system describing a disjoint union as arises, for example, in decomposition, then at low energies, one sees multiple 4-dimensional universes, each with its own separate metric and graviton, which are not mutually interacting. For this reason, we refer to the summands of decomposition as universes. Now, what I'm going to do first is warm up by describing some general features of sums of quantum field theories, and then I'll move on to describe the theories that motivated the work I'll describe today. So first, what does it mean for one quantum field theory to be a sum of other quantum field theories? How can I tell whether one quantum field theory is secretly a disjoint union? Well, one thing it means is that there should exist a complete set of projection operators. The theory needs to contain some topological operators that act as a complete set of idempotents. The product of any two different projection operators vanishes. The product of any projection operator with itself just is the projection operator back again. And the sum of all the projection operators is an identity. And then given such a set of projection operators, correlation functions can naturally be decomposed into correlation functions in a sum of the constituent theories, as is outlined there. So there's a math analog of at least part of this, and we'll see some other details later. If a space has m connected components, then its degree zero cohomology, of course, is m-dimensional. There are multiple degree zero elements of cohomology, and these topological operators I'm referring to can usefully be thought of as, in mathematical terms, as elements of degree zero cohomology. Now, what else does it mean for one field theory to be a sum of other field theories? Well, if our spacetime is connected, something else it means is the partition functions decompose. So for audience members who aren't versed in this language, a partition function is essentially a weighted sum over states of the theory, weighted by an exponential of the Hamiltonian. And so if the field theory is secretly a sum of several field theories, then one thing it means is that the partition function, that sum over states, should decompose into a sum of several sums of states, one for each of the constituent field theories. And then finally, in d space-time dimensions, for a theory to decompose means it has a possibly non-invertible d-1 form symmetry. I'll come back to that in a few minutes and explain what exactly I mean by a d-1 form symmetry. Now, what sorts of field theories can admit such a decomposition? What sorts of field theories are we going to be messing with here? Well, the field theories I'm interested in, which will have a decomposition, are two-dimensional quantum field theories. Quantum field theories on a space-time of dimension 2, with what are called global one-form symmetries. And these things have several equivalent descriptions. So for example, gauge theories with trivially acting subgroups, if the gauge group has a trivially acting subgroup, turn out to be examples, as I'll review in a couple of minutes. Another example is a theory with restrictions on instantons. If I take a gauge theory or a nonlinear sigma model and perform some sort of restriction, if I only permit some of the instantons to appear, that is also going to give rise to a theory of the sort I'm describing here. So another more abstract description is as a sigma model on something called a gerb. So mostly I'm going to avoid this language, but occasionally it might be helpful, and given the wide audience, there may even be a handful of people for which this is a useful language. A gerb is basically a fiber bundle in which the fibers are groups of one-form symmetries. And those groups, as I'll come back to in a few minutes, are denoted either BG or G with a superscript 1, depending upon whether you're coming from the math community or the physics community. Now, we'll see in this talk how decomposition into these universes I mentioned relates these different pictures of two-dimensional theories with one-form symmetries. For example, that restriction on instantons I mentioned can arise as an interference effect between the different quantum field theories in the sum. For another example, the one-form symmetry I mentioned of the quantum field theory can be thought of as a translation symmetry along the fibers of that gerb. A sigma model on a bundle has a translation symmetry corresponding to translation along the fibers of the bundle. Same thing is true here. And then finally, this business about gauge theories with trivial group actions is relevant because the prototypical group of one-form symmetries, BG, can be described as just a point modulo G, a G orbifold or a G gauge theory in which G acts trivially. So if that's the sort of canonical example, then it's natural that gauge theories with trivially acting subgroups should fall into this characterization. Now, another thing decomposition will do for us is that it solves certain technical issues with these theories. For example, we don't usually restrict instantons in a quantum field theory. As Weinberg taught us many, many years ago, this violates the cluster decomposition axiom of quantum field theory. So the fact that these theories are equivalent to disjoint unions solves that problem in the sense that a disjoint union also violates cluster decomposition, but in a completely mild and fashion that is trivially easy to understand. All right, so far I've outlined the theories that are going to decompose, and I've spent a lot of time talking about one-form symmetries. So the next thing I want to do is explain what is a one-form symmetry. Well, for this talk, intuitively, a one-form symmetry will be, well, something like a group, more nearly a two-group, but let's just call it something like a group that exchanges the non-perturbative sectors. And for this talk, by non-perturbative sectors, I'm going to mean either instantons or bundles, and I'm going to gloss over any distinction between the two. So for example, let's consider a gauge theory in which the massless matter is invariant under some non-trivial subgroup of the gauge group. And for the moment, I'm going to assume that subgroup is finite and abelian, and in fact, I'm going to assume it lies in the center of the gauge group. Then the non-perturbative sectors of that gauge theory, the G bundles in the spacetime, are invariant under the permutation given in the middle of that slide. I can take a G bundle and in some sense tensor in a K bundle to get another G bundle. And in so doing, that will give me a permutation of the G bundles into one another. Or put another way, at the level of gauge fields, if I take one G gauge field and roughly speaking, add in a K gauge field, that will give me a new G gauge field, which represents some permutation of the allowed instantons. So this is the symmetry. This is what a one-form symmetry means in this particular example of a quantum field theory. It's an action of a group of K bundles, where again, I'm using the word group a little bit loosely. And that group will be denoted either BK or K superscript 1. I'm usually going to use the notation BK in this talk. Now, next, let's see how decomposition works in theories with symmetries of this form. So let's suppose we have a G gauge theory. For simplicity, let's assume G is semi-simple with some finite subgroup acting trivially. And just to keep things simple, let's assume that subgroup lies in the center. As I've just discussed, that theory has a BK one-form symmetry that interchanges the non-perturbative sectors. Now, so far, this sounds like just one quantum field theory. A quantum field theory with some exotic symmetries, but still just one of them. What I'm going to do next is outline from another perspective how quantum field theories of this form are also each a disjoint union of other quantum field theories. They decompose. It's just a matter of perspective. So I claim this theory decomposes. One of the first property I mentioned of a theory that decomposes is that it admits projection operators. So where are those projection operators? Where are they hiding? Well, the fastest way to get there runs through math. I'll build these more explicitly in a specific concrete example later, but first let me just give you the general picture of where these are coming from. The projection operators, which you can think of as, well, twist fields in an orbifold sense or Gukov-Witten operators, are technically corresponding to elements of the center of the group algebra. So the elements of that center are all going to define topological operators in this quantum field theory. And there's a well-known math result that the center of the group algebra decomposes. That's essentially Wedderburn's theorem. It can be given a basis in the form of a set of complete orthogonal idempotents. Those idempotents turn out to be exactly the projectors onto universes. And for mathematicians in the audience, the way this dictionary works is that these different universes can be identified with, at least in this case, irreducible representations of K. So that, at a schematic level, is where the projection operators come from. Next, let me talk about the partition functions and this business about restricting instantons. So in these particular theories, the statement of decomposition is that the quantum field theory of that gauge theory above is the same as a disjoint union of quantum field theories of G mod K gauge theories with what are called discrete theta angles. For a talk at this level, I won't have the time to explain in detail what a discrete theta angle is, but suffice to say it's a phase factor that I can add to the contributions arising the path integral. For example, a pure SU2 gauge theory will be a sum of two SO3 gauge theories differing by a choice of discrete theta angle. The discrete theta angles will give a phase that couples to, well, technically the second Stiefel-Whitney class. I'll come back to that in a second. Perturbatively, an SU2 theory and an SO3 theory is, in this context, is identical. The differences between them are all non-perturbative. So what are those differences and how do they figure into this? Well, the SU2 instantons or bundles are a subset of the SO3 bundles. Specifically, they're basically the SO3 bundles of vanishing second Stiefel-Whitney class. The effect of the discrete theta angles is to weight contributions from the SO3 bundles of non-trivial second Stiefel-Whitney class by a sign. So if I take a sum over all the SO3 bundles, and I take another sum over SO3 bundles, but where the contributions from the SO3 bundles that can't be lifted to SU2 comes with a sign, then the effect will be to essentially cancel out the SO3 bundles that don't come from SU2. In other words, summing over the SO3 theories projects out some of the instantons, giving rise to the SU2 theory. This is how this decomposition works in this particular case. So let me try stating that a little bit more succinctly. So formally, the partition function of the disjoint union can be written as a sum. So that sum on the outside is the sum over components in that disjoint union. And then everything else on the inside is a path integral corresponding to each of the G mod K gauge theories. Now, if I move that sum inside the path integral, then what I get is, well, what do I get? I get something that looks like a projection operator. The effect of summing over the different components, summing over the different universes, is to enforce a projection. It projects out the SO3 bundles that come from SU2 bundles. So if the theories are perturbatively the same, if the only difference is in the non-perturbative sectors, and we project out any non-perturbative sectors that don't come from the SU2 theory, then what we're left with is, functionally the SU2 theory. So this is what we mean when I sort of laughingly refer to multiverse interference effects. The sum over the different SO3 universes is projecting out components that don't come from SU2. So schematically, two theories are combining to form what looks like a distinct third. So in this case, I can imagine two SO3 universes differing by a choice of discrete theta angle, which combine to form an SU2 theory. And then the SO3 bundles that don't arise from SU2 cancel out when the theories are combined. Now, so far, I've just sort of hand-waved my way through this at a very formal level. Let me give a little more detail in the case of SU2 theories. Let me quickly check these claims for pure SU2 Yang-Mills theories in 2 dimensions. Now, happily, pure Yang-Mills theories in 2 dimensions have a beautiful and very simple description due to Migdal and Rusakov from long back when. The partition function on a Riemann surface of genus G can be written as a sum over representations of the group weighted by factors involving the dimension of the representation and the exponential of, well, the product of the area and the second Casimir of the representation. So, this is easy to do. The partition function for SU2 is written there. It involves a sum over all SU2 representations. The partition function of the SO3 plus theory has the same form, except it involves a sum over the SO3 representations, which are a subset of SU2 representations. So the missing ingredient is the partition function for the SO3 theory of non-trivial discrete theta angle. That was written down years ago by Tachikawa, and that turns out to be a sum over the SU2 representations that are not also SO3 representations. And just from adding these together, it's clear that if you add together the partition functions for the SO3 plus and the SO3 minus theories, the result is literally the same as the partition function for the SU2 theory. And this extends to other simple gauge groups. It's straightforward, but the details are beyond the scope of what I can do in this talk. So that in a nutshell is decomposition. I'm going to come back and walk through the details of an example to make this all more concrete. But first, I wanted to sort of quickly walk through the literature. Over the last 15 years now, we've actually checked decomposition in many different examples in many different ways. For example, we can see this in gauge linear sigma models, in mirror constructions, and in quantum cohomology rings, as computed, for example, from the Coulomb branch. In Orbifold, decomposition can be seen in partition functions, massless spectra, elliptic genera. In fact, I'll work through an Orbifold example in a few minutes because with Orbifolds, one really can see absolutely everything explicitly. This arises in open strings and K-theory. There's a notion of K-theory of gerbs. The K-theory of a gerb decomposes into a disjoint union of K-theories of underlying spaces twisted in the right way. So this was a known math result from way back when that has a natural understanding in terms of decomposition. For supersymmetric theories in 2 dimensions, localization can be used to verify decomposition in detail. For non-supersymmetric pure Yang-Mills theories, as I've just outlined, this can also be seen in general. More recently, there's been some work on adjoint QCD2 by Zohar Kamargadsky and various collaborators. And there are also analogs of this in other dimensions, I'll come back to briefly towards the end. For example, in 4-dimensional theories with 3 form symmetries, there's a version of decomposition as well, which has been explored by various authors. Now, this is more than just some abstract observation about quantum field theories. It also has some fun applications. Hang on just a second. Sorry, the connection on my laptop, between my laptop and the iPad I'm running this on seems to have broken down for just, seems to have broken down. Let me take just a minute, stop sharing and restart to hopefully get that going again. There. So the applications I mentioned. So one thing this does is make predictions for Gromov-Witten theory. There's a notion of Gromov-Witten theory for gerbs. Decomposition makes a specific prediction, basically that the Gromov-Witten invariance of a gerb should be a sum of the Gromov-Witten invariance of the underlying space, which was checked years ago by various mathematicians. This can be applied to give some non-perturbative constructions of geometries in gauge linear sigma models, which is now sort of a standard trick in the GLSM community. This can be used as a tool to compute elliptic genera. And most recently, we've used it to work on anomalies. At the end, I will come back and briefly discuss these applications. But first, to make this concrete, let me walk through an example in an orbifold where absolutely everything can be made completely explicit. So let's consider an orbifold of a space by D4. That's the 8-element dihedral group. And let's take the Z mod 2 center of D4 to act trivially. For reasons I've already discussed, this theory has a BZ2 one-form symmetry because there's a trivially acting Z2 in the center. Now, since the quotient of D4 by Z2 is Z2 cross Z2, it's natural to expect that this should be related to a Z2 cross Z2 orbifold, and indeed, decomposition predicts that the field theory of this orbifold should be the sum of the field theories of a pair of Z2 cross Z2 orbifolds, with and without discrete torsion. There's a general formula that makes a prediction for decomposition in all cases. I don't have time to discuss it. This is just the consequence when that general formula is applied to this special case. So let's see how this works in this case. We can compute the partition function at genus 1 very explicitly. The partition function basically looks like a sum over all commuting pairs inside D4, where each commuting pair gives rise to a path integral over maps subject to certain boundary conditions. Now, since the Z2 acts trivially, these path integrals with boundary conditions are symmetric under multiplication by elements of the center. So the contribution from GH is the same as the contribution from GZH, is the same as the contribution from GHZ, and so forth. Now, these different sectors basically correspond to the non-perturbative sectors in the orbifold. These correspond to non-trivial D4 bundles over the world sheet. And we see that due to the fact that the Z acts trivially, these things are symmetric, and more to the point, these bundles are all related by tensoring in Z mod 2 bundles. So this is the BZ2 one-form symmetry explicitly in this particular case. Now, each D4 sector that appears is the same as a Z2 cross Z2 sector, appearing with the multiplicity 2 squared, with the exception of 3 sectors which don't appear. The reason they don't appear is that their pairs do not lift to commuting elements of D4. Z2 cross Z2 is abelian, D4 isn't. Not every commuting pair inside Z2 cross Z2 can arise from a commuting pair inside D4. So here we see a restriction on non-perturbative sectors. We've chopped out some of the non-perturbative sectors of D4. Well, we can compute the partition function explicitly. It's just a combinatorics exercise given what I've told you. It turns out to be twice something that's sort of almost the partition function of a Z2 cross Z2 orbifold, except that some of the twisted sectors have been truncated. So, another comment is that this is a different theory than the Z2 cross Z2 orbifold. Furthermore, discrete torsion acts as a sign on the sectors that were omitted. If I take the Z2 cross Z2 orbifolds with and without discrete torsion and just multiply the and take into account discrete torsion, the effect of adding those two partition functions together is to cancel out or project out the sectors that are omitted in the D4 orbifold. This is, again, what I mean by an interference effect in this context. So the result, the partition function of the D4 orbifold is a sum of partition functions of Z2 cross Z2 orbifolds, precisely matches the prediction of decomposition. Now that's fine for partition functions. I haven't said anything about projection operators, but they can be computed easily. If I denotes the dimension 0 twist field associated to the trivially acting generator of the Z2, the projection operators on the two universes take the form shown. And this can also be computed abstractly in terms of Wedderburn's theorem. Those two projectors are the same things you get from Wedderburn if you just plug in the two irreducible representations of Z2, but that's beyond the scope of what I can do today. So massless states. There's a straightforward algorithm to compute the massless states in an orbifold. If we apply that to T6 mod D4, then we get the states as shown. I've illustrated in the form of what's called a Hajj Diamond. Now, if we didn't know about decomposition, the 2's in the corner would be a problem. Perhaps not quite as big a problem as that I've illustrated there, but a problem nonetheless. The trick is they signal a violation of cluster decomposition, the same axiom that's violated by restricting the instantons. Now, under ordinary circumstances, if I could do a massless spectrum computation and got twos like that, I would assume that whatever I was doing, I would assume the computation was wrong. I would assume that I'd made a mistake somewhere. But it turns out to be correct, and decomposition saves the day. Because when I work out the massless states of the two Z2 cross Z2 orbifolds of T6 with and without discrete torsion, it turns out their sum gives rise to exactly that Hajj diamond. So again, this all matches decomposition. Now, in the cases I've discussed so far, the universes are all approximately the same. In general, they can be different. It's somewhat beyond the scope of this talk, but for completeness, I'm going to mention it. For example, if I quotient a space by the 8-element group of quaternions and let a Z mod 4 subgroup act trivially, that Z mod 4 is no longer in the center. So this is a variation on the story I've discussed so far. Then it turns out that X mod the quaternions is a sum of 3 universes, 2 of which are Z2 orbifolds and 1 of which is just X. So we still get a decomposition. Not all the components are the same. Technically, this has something called a non-invertible symmetry, but that's beyond the scope of what I can talk about today. So far I've talked about decomposition in 2 dimensions. What about other dimensions? Well, there's been work in other cases. In 4 dimensions, theories with finite global 3-form symmetries are also believed to decompose, and I've listed a few relevant papers there. And it's been conjectured that the same should be true for quantum field theories in D dimensions with finite global D-1 form symmetries. So in just a little bit more detail, this is mostly beyond the scope of what I can hope to do today. Schematically, the idea is that if you have a finite global D-1 form symmetry, that's going to involve a D-1 form, which will couple to a domain wall. And so there's a story here that's somewhat analogous to Busso and Polchinski's old work on dynamically reducing cosmological constants. This is also consistent with reduction on a circle. If I have a D-1 form, a D-dimensional theory with a D-1 form symmetry, and I roll it up on a circle, then I get a D-1 dimensional theory that will have a D-2 form symmetry, which should also decompose. If the D-dimensional theory decomposed, its reduction on a circle also ought to decompose. So that works. Now, is there any math here? So let me briefly say a few words there. There's a mathematical interpretation of all of this in terms of gerbs. As I outlined at the beginning, a gerb is basically a fiber bundle whose fibers are copies of BG. Now, a sigma model on a gerb has a global BG symmetry, at least a sigma model on a banded gerb, but just to stick to elementary cases. Just as a sigma model on a G bundle has a global G symmetry, both arising from translations along the fibers of the bundle. Furthermore, BG is the same as a point mod G. So whenever a group acts trivially, it's natural to expect a sort of gerb structure or a one-form symmetry arising somewhere. Now, I got interested in all this way back when as possible sources of new string compactifications. Now, there are a bunch of issues with this. One has to figure out how to actually build the field theory. There are issues I've outlined with cluster decomposition. There are other issues I haven't mentioned about what the moduli are doing. There are questions about modular invariance and unitarity in orbifolds. There are issues with potential presentation dependence. There was fun to be had for a while, but what we eventually learned was that these theories are well defined, but are disjoint unions of ordinary theories, at least in 2-2 supersymmetric cases. So we don't really get any new string compactifications, unfortunately, but there are some other applications. So in the time remaining, I want to quickly run through 4 of my favorites. So 1, Gromov-Witten invariance. There exists a definition of Gromov-Witten invariance of gerbs. Decomposition predicts the Gromov-Witten invariance of gerbs should be the same as the sum of Gromov-Witten invariance of the constituent universes, and that has been checked in detail in a series of mathematics papers that was spearheaded by Seng and Jiang and various collaborators. Gauge linear sigma models. Just very briefly, consider the following example: a gauge linear sigma model for a 2 torus described as a complete intersection of 2 quadrics in CP3. So briefly, this is a U1 gauge theory with fields of charge 1 and fields of charge -2. And if I go to one point in the parameter space called the Landau-Ginzburg point, I have a superpotential that looks like a mass matrix. So away from the 0 eigenvalues, this looks like a sigma model on a CP1 with a BZ2 symmetry. Decomposition implies that because of that BZ2 symmetry, we really have a double cover branched over the points where some of the phi's become massless. And that's another 2 torus realized non-perturbatively. So just a couple more and I'm just about done. So another more recent application, we can use decomposition to predict elliptic genera of supersymmetric gauge theories using knowledge, for example, of infrared supersymmetry breaking for various discrete theta angles. So for example, for SUK mod ZK, it's known that SUSY is unbroken in the IR only for one particular value of the discrete theta angle. If SUSY is broken, the elliptic genus of a pure G mod K gauge theory should vanish. Decomposition implies that if we sum up all of the elliptic genera of all the G mod K gauge theories with different discrete theta angles, I should get the same thing as the elliptic genus of a G gauge theory. So this is actually sufficiently many equations that one can algebraically compute elliptic genera. So it turns out that if you do a little bit of work, the elliptic genus of an SUK mod ZK gauge theory turns out to be, well, the expression shown there. For k equals 2, this was previously computed by Kim, and Park, and Richard Eager and I got a paper out of brute forcing checks of this by using results on supersymmetric localization. There's a general formula for what elliptic genera ought to be in terms of some Jeffrey Kirwan residue computation. So if you just crank through those computations after lots and lots of scribbling, you will eventually get the same result that I've just illustrated in 3 lines, how one can compute using algebra. So one more application, anomalies. So this we just got some papers on relatively recently. Suppose we have an orbifold, but with an anomaly. Now, there are 2 ways to resolve it. There was some work done by Wang, and Witten, and also separately Tachikawa back around 4 years ago now. They came up with a beautiful story, some beautiful elaborate picture of how one could deal with this. Their idea was that you take the original anomalous orbifold group, you make it bigger, you extend it to a larger group with the property that the pullback of the anomaly is trivial, and then you turn on some phases in the resulting orbifold. In some fashion that is mostly beyond the scope of this talk, but it's some beautiful story. There's also a sort of a boring way to resolve an anomaly. We could make G smaller. If G is anomalous, maybe it has a subgroup that's not anomalous. So we could imagine just replacing the original anomalous orbifold with an orbifold by a subgroup, which is non-anomalous. You know, it's boring, but that would fix the anomaly. One of the predictions of decomposition is that the fancy complicated way in which you make the orbifold group bigger is actually the same thing as the boring way in which you make it smaller, at least in 2 dimensions. In fairness to Wang, Witten, and Tachikawa, they were also interested in orbifolds in other dimensions, but at least in 2 dimensions, the sophisticated method and the simple method are in fact equivalent to one another. Making the orbifold group bigger is the same as making it smaller. And finally, this isn't precisely an application, but let me mention that these same structures also arise in modulized spaces, superconformal field theories. The modulized stack of supersymmetric sigma models turns out to be, on Calabi-Yal's, turns out to be a Z2 gerb over the modulized stack of Calabi-Yal's themselves. There's a structure that pops up in supergravity called the Bagger-Witten line bundle, which turns out to be what's called a fractional line bundle over that gerb. This arises even in moduli spaces of elliptic curves. We usually think of that as being a quotient of the upper half plane by SL2Z. The Bagger-Witten line bundle actually lives on a gerb over that moduli space. And in supersymmetric sigma models on elliptic curves, there's an extra Z mod 2 that extends T-duality, which gets reflected in the mathematics of that construction of the place where the Bagger-Witten line bundle naturally lives. But that's another story. All right, so let me summarize. So if you forget everything else about this talk, the one thing to keep in mind is that sometimes one quantum field theory is secretly a sum of other quantum field theories, and that sum can be used to understand various properties. Restrictions on instantons arise from such sums as interference effects between the different summands. Such theories typically have one-form symmetries, and can be thought of as arising from sigma models on gerbs, which are basically fiber bundles with fibers that are groups of one-form symmetries. And examples include gauge theories with trivially acting subgroups. And this has fun applications in Gromov-Witten theory, gauge linear sigma models, elliptic genera, and most recently anomalies. And that's it. Thank you very much for your time.
Thank you. Okay, any questions? Tristan?
I was actually just clapping, but I do have a question. On that D4 related orbifold, Eric, that you mentioned. Conspicuously, your two Hajj diamonds of the two models into which it decomposes are mirror of each other.
Yeah, it's not a general statement. It's just about that particular example. So let me, for everyone else, let me see if I can quickly page back to, yeah, here we go. So indeed, you're absolutely right, but it's just, I didn't mention it because it's a dumb fact specific to this example. It doesn't, to the best of my mind, it doesn't generalize in any natural fashion. It really just reflects the fact that this particular example is especially symmetric.
Okay, thank you.
That's all right. Other questions?
Okay, if there are no further questions, then let's thank Eric again for a great talk. And of course, we will convene again tomorrow.